Welcome to the deep dive. Today, we're tackling something really practical.
Yeah. What have we got?
We've got a set of practice questions for the Huawei HCSA-IP Network certification. You know, the H19301 V4.0 exam.
Ah, okay. Good stuff. So certification prep material.
Exactly. Think of it like a way to get under the hood of core networking concepts
Mm-hmm.
and maybe get a feel for how enterprise networks are actually built.
Right. And we're not just going to read answers, are we?
No, we're dissecting them, pulling out the actual principles of IP networking these questions touch on.
And looking at why they matter, in the real world. Our goal really is to turn these exam questions into some solid, usable knowledge for you.
Covering the basics right up to, well, how companies like Huawei approach things.
Sounds good. So where should we start? Routing, OSPF.
Yeah, let's do that. Our first question dives right into OSPF, open shortest path first.
Okay.
And the correct points it highlights are, 1, OSPF uses areas for optimization, and 2, it supports manual route summarization at ABRs.
Right. Area border routers.
So areas. It makes me think of like organizing things, keeping stuff tidy. But why is splitting a network into areas so important for OSPF?
Well, it really comes down to scale,
Right.
Imagine a really massive corporate network.
Yep.
Without areas, every single router would just be flooded with information, details about every link, every segment.
That sounds like a lot of overhead.
Exactly. Huge processing demands and really slow convergence times. That's how long it takes the network to figure things out after a change happens. So the key insight here is that areas weren't just like a nice add-on. They were fundamental. It's what allowed OSPF to scale up to handle huge enterprise networks, even parts of the internet, by setting up these logical boundaries. Limits the flood of routing updates.
Got it. So manageability and keeping the network quick to respond.
Pretty much.
And this manual summarization at the ABRs, how does that fit into the bigger picture?
So, tying this back to efficiency, summarization is all about controlling the routing info that flows between these areas. An ABR, sitting right there on the edge of an area, you can configure it to basically advertise a condensed version, a summary of the routes inside its area to all the other areas.
Right, like a table of contents instead of the whole book.
Exactly. Perfect analogy. It drastically cuts down the size of routing tables everywhere else in the network. Again, boosting efficiency, making the whole system more stable.
Okay. Now, the question also had some wrong options. It suggested OSPF is a distance vector protocol and that it relies on TCP. Why are those off base?
Yeah, that touches on a really crucial difference between routing protocols. OSPF isn't distance vector, it's a link state protocol.
Link state meaning?
Meaning routers share info about the state of their direct connections, their links. This lets them build up a complete map, like a topology, of the entire network area. And then they use this clever algorithm, Dijkstra's algorithm, to figure out the absolute shortest paths.
Right, not just distance and direction like distance vector.
Precisely. And as for TCP, nope. OSPF has its own built-in way to handle reliable updates. It runs directly over IP.
Stolen mechanism.
Yeah, often called a reliable flooding mechanism. OSPF routers make sure other routers in the area get those link state updates reliably. They use acknowledgements, retransmissions, all at the OSPF level. No need for TCP's whole connection setup and teardown thing. More efficient for this purpose.
Okay, that clears things up quite a bit. Makes sense. Right, let's move down the stack a bit. OSI Layer 2, VLANs.
Okay.
Question 2 asks which device works at Layer 2 and supports VLAN configuration. The answer is a Layer 2 switch. Seems simple enough, but let's unpack that.
Sure.
So we talk about routing between networks. What about splitting up a single physical network logically?
Right.
That's where VLANs come in, right? At Layer 2.
Exactly. A Layer 2 switch, it operates at the data link layer. Its main job is forwarding traffic based on MAC addresses, physical addresses.
Right.
But the game changer, what makes it essential for modern networks, is its ability to do virtual local area networks.
The VLANs.
Virtual LANs. The key thing, the real insight, was that VLANs let you create logical segments on top of your existing physical wires and switches. It just revolutionized network design. Suddenly you had flexibility, better security, and it was cost-effective because you didn't need totally separate physical gear for every department or group.
Okay, so how does that actually work? How does a Layer 2 switch create these separate networks inside itself? It's all the same hardware.
Yeah, it's clever. It works by adding a tag to the Ethernet frames as they come into the switch, usually using the AKE 802.1Q standard.
802.1Q. Got it.
This tag basically has a VLAN ID number. It marks which virtual network that frame belongs to.
Like a label.
Pretty much.
Yeah.
Then the switch looks at that tag and makes sure it only sends the frame out to other ports that are configured for that same VLAN ID.
Ah, so it keeps the traffic contained within its logical group.
Exactly. Effectively creating these isolated broadcast domains, these separate little networks, all within the same physical switch infrastructure. It's like logically carving things up.
Okay. The other options in that question were firewall, router, and core switch.
Yeah.
Just quickly, where do they typically play?
Sure. A firewall that usually operates higher up, layer 3, the network layer, and even above. It's focused on security, looking at IP addresses, ports, sometimes even application data.
Makes sense.
A router, its primary job is layer 3, routing traffic between different IP networks. That's its core function.
Right.
And a core switch. Well, these are often beefy devices in the center of a large network. They do high-speed layer 2 switching, but many core switches also have layer 3 routing capabilities built in, but fundamentally their main speed advantage is at layer 2.
Okay, good distinction. All right, question 3 takes us into Huawei-specific tech, their Air Engine product family.
Ah, the wireless side.
Yeah. The answer says it's for enterprise-grade wireless access and indoor Wi-Fi. So what's the main takeaway about Air Engine?
Well, the key thing is that Air Engine is Huawei's line specifically designed for the tough demands of business wireless enterprise environments.
So not just your home router.
Definitely not. It means it's built with features for handling lots of users simultaneously, providing really solid, reliable coverage, and using advanced Wi-Fi tech optimized for business needs, like specific applications or higher density areas. High performance is the goal.
Okay. The question also threw out NetEngine, Cloud Engine, and Ocean Store. Just for context, what are those families about?
Right. Good to know the portfolio. NetEngine, that's Huawei's router line. Think high-performance routers for service providers, big enterprises, core network stuff.
Got it. Routers.
Cloud Engine, that's their data center switch series, built for the massive bandwidth and super low latency you need in modern data centers, cloud computing environments.
Which is for the cloud. Okay.
And Ocean Store, that's storage. Their whole family of storage products covering pretty much everything an enterprise might need for managing its data.
Right. So routers, data center switches, storage, and wireless with Air Engine. A whole suite.
Exactly. Covers the main infrastructure pillars.
Okay, cool. Let's shift back to fundamentals. Private IP addressing. Question 4 asks about the private ranges defined back in RFC 1918.
Ah, yes, a classic.
The correct ranges listed are 192.168.0.016,
The home network special,
0.10.0.0.08,
the big enterprise one.
and 172.16.0.016.
Yeah.
Why do we even have these private addresses? Why not just give everything a unique public address?
That is such a fundamental point. The whole concept of private addressing, defined in RFC 1918, was incredibly insightful. It basically acknowledged that, hey, not every single device on Earth needs a globally unique, routable IP address.
Right. Like my printer doesn't need to be directly reachable from, anywhere on the internet.
Exactly. And this was crucial. It prevented the exhaustion of IPv4 addresses years ago. Without it, the internet's growth might have just, stalled. These private ranges, they're not routable on the public internet, so organizations can use them internally however they want without worrying about conflicts with anyone else.
And then we use NAT, Network Address Translation, to let those private devices talk to the outside world.
Precisely. NAT acts like a gatekeeper, usually on the firewall or router. It lets many devices with private IPs share a small number of public IPs when they need to access the internet. It translates the addresses back and forth. Absolutely key technology.
Okay. The question also kind of hints at typical uses for each range. You mentioned them briefly, but can you elaborate just a bit?
Here, so the 192.168.0.016 range, that block gives you about 65,000 addresses, but it's often carved up into smaller 24s. Very common for home networks, small offices, easy to manage.
Okay.
The 10.0.08 range, that's huge, over 16 million addresses. So you typically see this used by large corporations, organizations with really extensive internal networks needing lots of subnets.
Right, gives them loads of room.
And the 172.16.0.012 range that sits in the middle, it provides just over 1 million addresses, so often used by medium-sized companies or organizations.
Okay. And one of the wrong answers was 172.32.0.012. So just to be absolutely clear, that third private block, it starts at 172.10.0.0.
Yep.
And the 12 mask means it goes up to...
It goes up to 172.31.255.255. That 12 mask covers 16 consecutive 16 blocks from 0.16 up to 0.31. So 172.32.0.0 is just outside that defined private range.
Got it. Crystal clear. Okay, question 5 loops. back to Huawei again. Their iMaster NCE platform, focusing on O&M.
Operations and maintenance, yeah, the management side.
Right. The correct features listed were automatic topology discovery, centralized device management, and visualized fault diagnosis. Uses AI, apparently. What's the main advantage of having a platform like iMaster NCE to manage your network?
Well, if you think about managing modern networks, especially large ones,
Yeah.
the core benefit is really automation and simplification.
Okay.
Imagine trying to keep track of thousands of devices, switches, routers, firewalls, access points, manually mapping it all out, configuring each one individually, trying to figure out what broke when something goes wrong. It would be, well, a nightmare, incredibly slow, and you'd make mistakes.
Yeah, it doesn't scale well manually.
Not at all. So this automatic topology discovery feature, basically the platform goes out and maps your network for you.
So you get a live picture.
Exactly. A clear, up-to-date view of your infrastructure makes it way easier to see how things are connected and spot potential problems fast.
And the centralized management part.
That lets you push out configurations, software updates, security policies, all that stuff to potentially hundreds or thousands of devices from one single place. Huge time saver, ensures consistency.
Okay. And the AI in the visualized fault diagnosis. How does that help fix things faster?
So this is where things get pretty interesting. The AI aspect means the platform can analyze just massive amounts of data coming from the network logs, performance metrics, alerts.
Looking for patterns.
Exactly. Looking for patterns, anomalies, things that might signal a problem brewing, or correlating different events together to figure out the root cause of a failure much faster than a human probably could, sifting through all that data.
And the visualization.
That presents all this complex analysis in a hopefully intuitive way, like graphical charts, diagrams showing you where the problem is, maybe even suggesting steps to fix it, guiding the admin.
Okay. The question also mentioned something about reducing power consumption via AI chips, but that wasn't listed as a key O&M feature here.
Right. It highlights that you need to focus on what the platform is specifically stated to do for operations and maintenance in this context. While AI might be used elsewhere, those three, discovery, centralized management, and AI-assisted fault diagnosis, are the core O&M capabilities mentioned.
Gotcha. Okay, last question. Number 6 takes us right back to basics. The TCP/IP model.
The foundation.
Yep, reminds us it has 4 layers: application, transport, internet, and network access.
Sometimes it's called link layer, that last one.
Right, and it notes key protocols. IP works at the internet layer, TCP and UDP are at the transport layer, and things like HTTP and FTP are up at the application layer. Anything crucial we should add about this fundamental framework?
Well, just emphasizing how absolutely essential it is, the TCP/IP model really is the blueprint for how pretty much all modern network communication works, especially the internet. Understanding these layers and which protocols do what at each layer is just fundamental for anyone in networking.
Yeah, you can't really troubleshoot or design networks without it.
Not effectively, no. So application layer, that's where your apps live, your web browser using HTTP, your email client, file transfers using FTP, it talks to the network.
Okay.
Transport layer below that, that's TCP and UDP, providing that end-to-end connection service between applications. TCP gives you the reliable, ordered delivery. UDP is faster, connectionless, fire and forget.
Right, different tools for different jobs.
Exactly. Then the internet layer, that's IP's home turf,
Oh.
all about addressing packets with IP addresses and routing them across potentially many different networks to get them to their destination.
The inner networking part.
Precisely. And finally, down at the bottom, the network access layer or link layer. That handles the gritty details of actually transmitting the bits over the physical medium. Ethernet cables, Wi-Fi signals, whatever it is.
Putting the data onto the wire, basically.
Yep. So just keeping straight, which protocol belongs to which layer helps you visualize that whole journey data takes from one application down the stack, across the network, and back up the stack on the other side. It's key.
Okay, fantastic.
Talked about the routing protocols like OSPF, the layer 2, switching with VLANs, the wireless access points, the IP addressing scheme, the management systems like NCE, how they all have to interconnect and work together perfectly.
Right, it's a complex system.
It really is.
Yeah.
So what do you think are maybe some of the biggest challenges network administrators face today? Trying to keep these complex networks running reliably and efficiently with all these moving parts.
That's a good question. Balancing performance, security, cost, new technologies.
Exactly. It's a constant juggling act, making sure all these different technologies play nicely together. Definitely not a simple job. Something to think about.